Hi everyone, this is your favorite tutor and I'm here to discuss linear regression with you, and I want to teach you how to do linear regression, quadratic regression, and cubic regression in Excel. But before we do that, I want to go over the basics of linear regression with you. And before we do that, I would really love it if you guys could smash that like button, hit subscribe so that I can make this content for you guys and continue making it for free. Thank you guys so much, and let's get started. Now let's say you are interested in determining whether there's a relationship between the weight and height of students in your classroom. And in order to do that, what you do is you randomly sample 5 or 6 students from your class and ask them what their weight and their height is, and then you plot it on a graph. So you have the graph, and you can kind of tell that there might be a positive relationship going on here, right? Like this looks like as x increases, maybe y increases, but you're not entirely sure. So in order to determine what kind of relationship we have going on here, we can use something called linear regression, or OLS for short. Linear regression is going to help us determine what kind of a relationship exists between the x variable and the y variable. The x variable is called the independent variable, or the regressor, and the y variable is called a dependent variable. This is because the x variable helps determine the y variable. So once you come up with that data, you're going to need to draw a line through it, and as I mentioned, that's going to require something called a linear regression. In order to do a linear regression, you're going to write the equation yi equals beta 0 plus beta 1 times x1 plus u. And I'll explain what each of these are in just 1 minute. So let's say that the linear regression tells you to come up with this line right here, which we're going to call the best fit line, okay? That is the best fitting line for all of these scatter plots, for this scatter plot and these particular points. And the reason that it's the best fitting line is because it minimizes the distance between the line and each of these points, okay? That's being minimized by this line, which we're going to call the best fit line. So that's what linear regression is basically doing when it comes up with this equation. Here, the beta 0 is going to be the y-intercept, so that's going to be where this line is going to intersect with our y-intercept. And then the beta 1 is the slope coefficient of this line. So the slope is, as we all know, the change in the y due to 1 unit change in the x variable, and that is beta 1. Now the u is something unique to linear regression. The u is actually going to be the difference between the predicted value of the y and the actual value of this point right here. Formally, we call the u the error term. So right there, I went ahead and drew what the u is going to look like. So that's going to be the distance between the actual value and what you would predict the value is based on this equation right here. The formula for ui is going to be yi, the actual value, minus y hat, the predicted value. So we know that linear regression came up with this line. How did it come up with this line and these beta values? Well, it went through and it minimized the sum of squared mistakes, okay? It found all of the y values such that you subtract the beta and the beta 1 from it in order to minimize this entire value. So that's called minimizing the sum of squared mistakes. And that really involves some upper level stats and calculus, so we're not going to get into it. But just know that it comes up with the beta 0 and the beta 1, the actual values, using the minimization of the sum of squared mistakes. And there's actual formulas for beta 0 and beta 1, which you can look up if you want in your free time at some point. But for our purposes, because Excel is going to already give us these values, we're not going to be that concerned for this particular lesson about how to manually calculate those. So now that we've figured out how to run a linear regression and how to fit a line along those dots, we are going to determine what makes one linear regression model or a specific model better or worse than another model. And the way we do that, there's a lot of ways, but two of the main ways you can do that is by looking at the betas and looking at something called the R-squared. So let's go over the betas and then we'll go over the R-squareds. So here, as you can see, we can do something called a hypothesis test on the betas to determine whether the betas are a relevant factor for determining the dependent variable. Okay, remember, we're trying to assess the relationship between x and y, and if there's a relationship between x and y, then beta 1 should not be 0. It shouldn't be 0 because if it is 0, what's going to happen to the relationship? It's not going to exist because beta 0, which is going to be, beta 1, which is 0, multiplied by x1 is going to lead to 0. So there isn't going to be no relationship. Now, the way to test that is to set up first something called a null hypothesis. This is called a null hypothesis. Beta 1 is equal to 0, and then the alternative hypothesis, which is that beta 1 does not equal 0. To determine which one of these hypotheses is true, whether HO is true or H1 is true, we're going to calculate the t-statistic. The t-statistic is calculated by the beta 1 minus 0, whatever the value is over here, divided by the standard error of beta 1. And if this value, TA, this is supposed to be an A here, and this is also supposed to be an A, is greater than the t critical value that we get from the t-table or the chart that's found in most statistics books, then we're going to reject HO. We're going to reject the null hypothesis in that case. And just remember, we reject null hypotheses. That doesn't mean we accept the alternative hypotheses. That doesn't mean we accept this hypothesis. What it does mean is that there's statistically significant evidence to reject that beta 1 equals 0, which means most likely there is some kind of relationship between the x variable and the y variable, so the independent variable has some kind of a statistically significant impact on the dependent variable that we're provided here. Another way to look up whether the beta here is going to be significant is to look up the p-value. And the p-value that you get for calculating the t-statistic, the TA, if that's less than 0.05, then we're going to say that there is significant evidence to reject the null hypothesis, to reject HO right here. Another method that we can use to determine whether one model is better than another or if a model itself is a good model is the value of R-squared. What R-squared is doing is it's taking the sum of y hat, which is the y determined on the line that we drew, so that's the y on the line, minus y bar, which is the average value of all the y observations that we took, squared, divided by the individual y observations, yi, minus, again, the average of all the y observations, squared. So for our purposes for this Excel exercise, it's going to do it all for us, but I just wanted to show you the formula. And there's a way to do it manually, which I'll hopefully be going through in another video, but for our purposes in this particular video, we're just going to keep it brief and just know that this is the formula, and this helps determine whether the model is a good model for the sample at hand or if it's not a good model for the sample at hand. And the formal way to define R-squared is it's the percentage of the variation in y that is explained by the change in x. So the percentage of the variation in y that is explained due to the independent variables that are in our model. And we want that value of R-squared to be as high as possible. It is generally in the range of 0 to 1, not -1 to 1. So 0 to 1, and we want r squared to be as large as possible because that tells us that more of the variation in the dependent variable is explained by the independent variable. Now there's another value which we can use to determine how good a model is, which is the adjusted r squared. This one is really handy when you have multiple variables. Here in this formula, the n is going to be the number of observations you have, and k is the number of variables that are in your model. So generally what happens with r squared is it does have a flaw, is it increases generally as you add more variables to the model, as you add more x's, more independent variables to the model, r squared is going to increase. And in order to take away the impact of those additional variables, we'll use something called r squared, and that's going to give us a better comparison between 2 or 3 different models that might have a different number of x variables. Now, sometimes a linear regression is not good enough to help explain the variation in the y. And that's when quadratic and cubic regressions, together they're known as polynomial regressions, come into play. In a quadratic regression, you're basically taking the original variables in the linear regression, but you're also adding a quadratic term. So you're adding beta 0 plus beta 1x plus beta 2 times x squared into the model. And then for the cubic, you go to the next level and you add this variable, which is beta 3 times x cubed. So now that we've gone over this, I think we're ready to go ahead and head into Excel to actually produce these different types of models and kind of judge between the 3